The concept of the Big Bang has shaped how we understand the universe, laying the foundation for modern cosmology based on the theory of Einstein. The Big, also known as textbook cosmology bang, refers to the moment the universe began its expansion, marking the creation. This is the energy and existence of all matter. Event occurred approximately 13.8 billion years ago and led to the vast universe we observe today. However, recent cosmological advancements suggest that the Big Bang may not have been the absolute beginning. Instead, there could have been a phase before the Big Bang, which significantly contributed to shaping our understanding of the universe. This prephase is called cosmic inflation. One of the most fascinating phenomena is inflation. Aspects of the modern cosmology suggests that before the hot, dense period of the Big Bang, the universe underwent an extremely rapid growth. During this time, the universe increased in size at a staggering rate. To demonstrate just how extensive this expansion was, imagine that if the universe started smaller than an atom, it would have expanded to the point of being unfathomable larger than everything that can be observed. Universe in a fraction of a second or less, second approximately 1/4 of a second. This phase of inflation did not last long, but it played a crucial role in shaping the universe. After inflation ended, the momentum behind this expansion was released into space, heating it up and generating matter's particles that constitute everything in the universe. In many ways, inflation can be considered a forerunner of the Big Bang. While the theory of inflation is widely accepted in cosmology today, for instance, there are still unanswered questions. We do not yet know what caused, what stopped inflation, and how did it stop long it lasted. These are unresolved questions in cosmology, and providing responses to them is essential for deeper understanding of the origins of. Before inflation, the universe was an incredibly dense, tiny area that is frequently referred to as a singularity. From this singularity, inflation began, ultimately resulting in the formation of atoms, particles, stars, and planets. The notion that the universe began with the Big Bang, modern yet compelling. Everything cosmology points to a more intricate picture. Some theories propose that the universe went through a phase before the Big Bang. During this phase, inflation triggered the expansion of the universe at an extraordinary rate, growing by a factor of trillions in less than a second. This rapid expansion was driven by a mysterious form of energy that permeated empty space. Once inflation ended, the energy that had fueled this expansion transformed into particles, heating the universe and leading to the hot, dense state we call the Big Bang. This inflationary phase was empty and cold, but it set the stage for the formation of matter and the universe we observe today. One of the more speculative ideas in modern cosmology is the concept of eternal inflation. This theory suggests that inflation did not stop all at once. Instead, it ended in patches, creating multiple pockets, each of which could be its own universe. As per eternal inflation, our universe would be just one of these patches. In this scenario, there could be an infinite number of such universes, each with its own set of physical laws and constants. This is where the multiverse idea originated, comes into play. The idea that our universe could be one of many, or even part of an infinite number of universes. If this theory turns out to be correct, it would clarify the nature of our universe, finely tuned for life in this multiverse situation, and each and every possible combination of physical laws could exist in different universes, and we are merely a part of one, where conditions are perfect for stars, for the formation of and elements like carbon and oxygen to exist, which are essential for life, while theories like eternal inflation and the multiverse remain speculative. The possibility of inflation itself can be seen to be supported by evidence. Is the most convincing support for inflation comes from the cosmic background microwave radiation, CMBB. The oldest light in the universe, the CMBB, was released approximately 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. At this point, the universe became transparent. Additionally, This light has been moving through space ever since. By studying the CMBB, cosmologists can essentially take a snapshot of the beginning of the universe, providing clues about what happened shortly after the Big Bang and supporting the inflationary model. One of the most significant discoveries came from the European Space Ice Planck satellite, which captured detailed images. These images showed the CMB in a subtle variations in the temperature of the early universe, and these variations matched predictions made by inflationary theory. This experimental evidence strengthens the case that inflation is not just a theoretical concept but an essential part of how we understand the understanding of the universe's origins. The events that came before and after the Big Bang requires combining two of the most important theories in modern physics: Einstein's general theory of relativity and quantum theory. General relativity describes the large-scale structure of the entire universe, including the actions of galaxies, stars, and planets, while quantum theory describes the behavior of atoms and molecules at the smallest scales to answer fundamental questions in cosmology, such as the nature of the universe composed of and where it originated. Scientists need to develop a theory that unifies these two frameworks. This would allow us to comprehend not just the major bang, but also the conditions that led to it. Is one of the most amazing aspects of the universe is its size. The most distant objects we can observe are around 47 billion light-years away, meaning the observable universe is about this may be 94 billion light-years away. Seems strange considering the universe, how could it be, is only 13.8 billion years old. The observable universe be larger than the amount of time required for light travel across it in the universe's lifetime. The answer lies in the fact that the universe has been expanding over time. As the universe expands, the distance between objects increases, causing distant objects to be farther away than the amount of time necessary for light to reach us. Most scientists believe that the universe extends far beyond the observable universe. In fact, it's possible that the entire universe is infinite in size. The observable universe is simply the part we can see, limited by how long light has had to travel since the Big Bang. There may be vast regions of the universe that we will never be able to observe. While it's possible that the universe is infinite, the question remains, is there anything beyond the universe? Most scientists remain uncertain about this idea. Since the universe is infinite, there wouldn't be outside to it. The universe would simply remain constant. Even if the universe is finite, it might not make sense to talk about anything beyond it. Beyond would imply something that exists outside of space itself, is a property of the universe. Thus, the idea of beyond the universe may have no physical meaning. Just as the beginning of the universe is a subject of extensive research, so too is its final end the most commonly held current. It is estimated that the universe apart at an ever-increasing rate. If this acceleration continues, the universe will keep expanding indefinitely, eventually getting to the point where galaxies are so far apart that they are separated from each other. In this situation, the universe would become cold, dark, and exhausted. Stars would burn out, planets would drift apart, and matter would eventually decay. This fate is known as the Big Freeze or heat death of the universe. The story of the universe from the Big Bang to its possible end is one of the most profound and intricate narratives in science, despite the fact that learned a great deal about the origins of the universe through the theory of inflation and cosmic cosmology research. Microwave background. Many questions remain unanswered. What triggered inflation? What caused it to end? What lies beyond the observable universe? Is there a multiverse, and if so, how many other universes exist? As scientists continue to study the universe using advanced technologies and theories that combine quantum mechanics with general relativity, we will undoubtedly gain deeper insights into these mysteries. The quest to understand the universe is ongoing, and every discovery brings us one step closer to providing an answer to ultimate inquiries regarding our existence. The study of the universe's origins and structure is not only a scientific effort, but it also raises philosophical questions about existence, reality, and our place in the universe. Is crucial area of interest in cosmology is the nature of dark matter, which is thought to make up about 27% of the universe's mass energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, rendering it undetectable and only visible through its effects of gravitation on matter that can be seen. The ability to comprehend dark matter is crucial for describing the development and behavior of galaxies. Ongoing studies and observations have provided insights into dark matter's properties, but its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, axions, WIMPs, and other unusual particles, but there isn't any direct evidence of dark particles of matter have not yet been discovered. Through the search continues. Combination of terrestrial experiments, astrophysical observations, and simulations that model how dark matter influences the large-scale structure of the universe. Another key area of research is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy constitutes approximately 68% of the universe's mass energy content. Its discovery was unexpected and has led to numerous hypotheses, including the cosmological constant and dynamic fields such as quintessence. Understanding dark energy is essential as it will determine the final fate of the universe. According to scientists, are looking into its effects on the cosmic structures and attempting to ascertain whether it remains constant over time or evolves alongside dark matter, and the study of large-scale dark energy structure formation provides useful insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments have revealed how matter clumps together under the influence of forming the intricate structures by gravity we see today. Simulations run on supercomputers help researchers understand how these structures formed over the course of billions of years and continue to evolve. Astrobiology also intersects with cosmology as scientists seek to understand the conditions necessary for the search for life beyond Earth. Exoplanets, planets orbiting stars outside our solar system, has intensified over the past few years, with thousands of exoplanets discovered. Some of these exoplanets exist in their stars' habitable zones where conditions might be in order for there to be liquid water. By examining these far-off worlds, scientists hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet conducive to life. Finally, the role of fundamental cosmological physics cannot be overemphasized. The need for a unified theory that reconciles general quantum theory and relativity persists in posing a problem for physicists. Theories like string theory and loop. The goal of quantum gravity is to connect these two domains that provide justifications for phenomena like black holes and the early universe. Adapts to technological advancements. Our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are revolutionizing our ability to study distant galaxies and cosmic events, providing unprecedented detail. With each groundbreaking observation, we move closer to unraveling the mysteries of the universe's structure, evolution, and ultimate destiny. The study of the universe is a rich tapestry of scientific inquiry and philosophical reflection, and the persistence of humanity. Curiosity about the cosmos is a testament to our desire to understand the vastness and complexity of the universe.